Hey students, today I'm doing a quick little video on why do we use FOIL and why does the distributive property and rules like that when multiplying polynomials, why? You know your math teacher probably taught you how to FOIL, but maybe they didn't explain to you why the rule works the way it does. So there's a quick little visual way that I like to think about it. I'll show you guys in the video. But in case you don't know what foiling is, essentially if you have two polynomials, like say we have a binomial x plus 2, and it's multiplied by, say, x plus 4 or something, and want to calculate what the product of those two different things, x plus 2 times x plus 4, if we want to know what that is, the rule FOIL is a mnemonic to help us remember what we need to multiply. And essentially FOIL stands for four things, F-O-I-L, first, outside, inside, last. So first describes multiplying the first in both of the polynomials. Outside is the two outside terms, then inside is the two inside terms, and then last would be the last two terms. So basically we need to multiply all those four things together, and then those four things are added up. So I'll just finish the example, and then I'll try to give you a little reason as to why it works this way. So first would be x times x. X times x, remember, is not 2x, it's x squared. X plus x is 2x, so x times x is x squared. Then the outside would be x times 4 is 4x. And remember, we're adding these things together. Then inside is 2 times x, which is 2x, and added again. And then lastly, the last terms, 2 and 4, are multiplied, 8, and added. And of course, we sometimes call the outside and inside terms the inner product, those two things in the middle. With binomials like this, those two things often are like terms, and so we could add these two terms together in the middle, 4x plus 2x, which, as I'm sure most of you know, makes 6x. When you have like terms, we add the coefficients together. 4 plus 2 is 6, so we get plus 6x plus 8. And this is the end result of the foiling, and that gives us the product of those two polynomials. Factoring is the idea of undoing this. So if we're starting with a polynomial like our answer and we want to know how do we break it up into pieces, that's what the idea of factoring is. But that's a topic for another video. Anyway, so why is foiling? Why do we have to take all these products? It's a good question. So, and if you don't, there's a little visual way that I remember, I think of it and think of how to do it. Basically, if I drew a rectangle where one side, let's say, I'm trying to model the process of multiplying x plus 2 times x plus 4. And so I'm going to say one side of my rectangle is x plus 2. So if, let's say, this is one side of my rectangle, and this length here is, I don't know what this is, but let's call that x. And then the other portion down here is 2. Then that length of that side would be x plus 2. Again, x stands for, it's a variable length, so I know I drew it. It looks like it might be 4 or 5 or something, but just pretend x could be any length. That's kind of why we use x, to stand for something we don't know, and really generally stand for anything. So x is some variable. So if I want to take that x plus 2, which would be the length of that line segment right there, and I want to multiply it by x plus 4, well, as you probably most of you know, if you multiply two numbers together, visually how you could imagine that is you're finding the area of a rectangle of those sides as well. So 3 times 4 is equal to 12. Well, if you have a rectangle, one side 3, one side 4, the area of that rectangle will be 12 as well. But anyways, if I make the other side of my rectangle x plus 4, again, x, let's say x is that same length as the other x. Let me just try to draw it of the same length. Again, x could be anything. And then this side over here is 4. I'll try to make it approximately the right length, so in case that bothers any of you. So anyways, the second side of my rectangle, I'm just going to draw as size x plus 4. And again, the reason I'm going to do this is, well, if I kind of fill in the rectangle here and I complete the drawing of my rectangle like this, and we try to figure out what's the area of this rectangle, well, it should be one side, the length, times the width. In this case, we call the length x plus 4, this bottom segment down here. So sort of what I'm imagining is this is my length, the x plus 4, and then this guy over here is my width, x plus 2. And so if we look at how much area we would get if we multiply x plus 4 times x plus 2, and we want to sort of visualize that, basically if I kind of connect these rectangles in those, based on those little tick marks I drew, we could look at each little portion of this area. And of course, the total area of that rectangle should add up to the area of those 4 new little rectangles I drew. So essentially, x plus 2 times x plus 4 should be equal to all those four little rectangles I drew here. Well, if we look at this rectangle, this dimension should, on top, should match the dimension below, because property of rectangles at the same length on top as on bottom. Also, this guy here should be length x, and then this guy here should be length 4 and 4, and this guy would also be x and x, and then this length there would be 2 and 2. That's just a basic property of rectangle. So anyways, here's my point. If we look at the area of each one of these shapes, this one right here actually would form a square. If we look at x by x, if we look at this sort of portion that comes through, x by x would be a square. And so the area of that should be x times x, or x squared. And that's, again, why we call it x squared, because x times x you could visualize it as a square. But anyways, the area of this little portion in here in green will be equal to x squared. So I'm just going to write that over on the right, because that's the area of that guy. Then if we look at these other segments, so let's do the next segment in blue, this segment over here, the area of that, this would be a rectangle. It has length 4 and width x, or vice versa. But if we look at dimensions of that rectangle, one side is 4, one side is x. So one of those sides would be, the area of that rectangle would be 4 times x. If we move on to this third little rectangle down there, that has dimensions 2 by x. Again, so the area of that would be 2 times x, or 2x. And then finally, the last segment I'll do in purple would be down here. And if we look at this rectangle, well, that is 2 by 4. 2 times 4 is 8. So our last little portion would be 8. And so here's kind of the point. When we multiply a binomial, like in this case x plus 2 over on the left, when we multiply that by another binomial x plus 4, if we try to visualize what's happening with those sort of complex polynomials, we actually get a lot of different segments and portions. So basically, we have to make sure that we take every number in our binomial and multiply by every number in the other binomial. And that's kind of what FOIL is teaching us to do. We take the first and we multiply it by the first. And we also take it in the outside, we multiply it by that one as well. So I like to visualize this as a distributive property, x times the first, x times the second. And then we also take the 2, multiply it by the first and the second. And now basically is just the distributive property applied to every term in the first polynomial. And what happens is we will make sure that we don't leave out portions of that area. If you don't get all those products, what you're doing is you're missing actual portions of the product. Or like in terms of the visualization, this drawing I drew, if you miss out on some of those foils, you'd be missing out on portions of the area, so the product would not match up with the other thing. And this can be extended to past foiling, like if you had a trinomial times another trinomial, like a 3-term times another 3-term. How do you do that? So let's just kind of make up a quick example of that to end up this video with. But let's say we had x squared minus 4x plus 2, and that's times x squared plus 3x minus 5. And so FOIL doesn't really actually work here because there's too many terms, but the idea of FOIL will still work. Essentially, in our first polynomial, the first term in that needs to be distributed to every term in the second. So we need to multiply this by the first term and the second and the third. And then we would do the same for the second term. So we would take our negative 4x. It would be multiplied to each of these terms as well. And then lastly, our plus 2 would also need to multiply to each of those 3 terms. So we'd actually end up with 9 products. And if we drew these as kind of like what I did before with rectangles, it's hard to do with negatives, like with minus 4x. You might be wondering, how do I draw these things? So it won't work exactly the same way. But that's kind of how I remember I need to sort it out, make sure I have enough products. In this case, if our polynomial is 3 terms times 3 terms, we should end up with 9 terms. basically if you multiply the number of terms in your polynomials together, that should give you how many total products you should have after you fully multiply. But if we go ahead, let's just go ahead and finish this example. If we did our distributing in red there, we'd have x squared times x squared makes x to the fourth. X squared times 3x would make 3x cubed. X squared times negative 5 would be negative 5x squared. So those were my portions in red. Then the green distributing portions, I needed to do negative 4x. Remember, the negative distributes with the term. Negative 4x times x squared would make negative 4x cubed. Negative 4x times 3x would be negative 12x squared. Negative 4x times negative 5. Negative times negative is positive 20x. And then finally, the yellow terms, we would have plus 2x squared, plus 6x, and 2 times negative 5 is minus 10. And then finally, after all that, we would have, again, so notice there's 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. We then could combine the like terms kind of like with those. In this case, there's only 1x to the fourth term. There's 2x cubed terms. So we could add those together. 3 minus 4 would make negative 1x cubed. Then we have 3x squared terms. We could add all those together. Negative 5 plus a negative 12 is negative 17, plus 2 is negative 15x squared. We have 2 x terms. 20 plus 6 is 26x. And then our constant term is all by itself, so that would make minus 10. And then finally, the result of that trinomial times a trinomial would be that as well. And basically, this hopefully kind of get the picture and the idea of all those terms need to be multiplied. And if you want to remember why you got a FOIL, basically, if you miss out some of those products, FOIL is a way to help you remember that all those products need to be distributed to one another. If you don't, you're going to be missing out portions of your area. It wouldn't be the full product. You'd be missing some of them if you don't take all of them into account. So hopefully this makes some sense. Let me know if you have any questions in the comment board. Have a great day.